Good morning, guys. How are you today? Um, so today I'll be explaining the physics past papers for the final. Sorry for posting it a bit late, but I'll try to do as much as I can. Okay. So for question number 4, okay, for the first past paper, which is paper October-November 2021, we have question number 4. A power station uses wind energy to generate electricity. State and explain whether this method of generating electricity is renewable. First of all, we know obviously that this is renewable. So we know that it is renewable. Yeah, it is a renewable source of energy. Explanation is that wind cannot run out, so it cannot be used up, and it's an infinite source of energy. So statement is that it is a renewable source of energy. Why? Because wind is an infinite source of energy, meaning it does not run out. Okay, so we move on to part B. In part B, it says state 2 energy resources that do not have the sun as their source. So there's 3 energy resources that do not have the sun as their source. We have geothermal energy, nuclear energy, and tidal energy. You can put any of these. So, for example, you can choose geothermal energy, which is the energy of the Earth, or the energy coming from the Earth, and nuclear energy, which is the energy of nuclear reactions. Now part C, for each energy resource, state the form of energy stored in fossil fuels and water behind hydroelectric dams. So fossil fuels, we know that it stores what? It stores chemical energy. So if they ask you the energy resource that is stored in fossil fuels, it is then chemical energy. Okay? However, if they ask you the water behind hydroelectric dams, how does this work? This works by storing the water in the dam until it has a lot of gravitational potential energy. Then it will fall with the kinetic energy from the dam, and it will turn the rotor, or the I don't know what to call it, just the rotor, and it will function the electric generator to make electricity. So very simply, water behind hydroelectric dams, it is what? It's stored as gravitational potential energy. Okay, so this is it for the first paper, I believe. So now we move on to the next paper, or not the next paper, the next question, which is question number 5. In question number 5, it says, a thermocouple thermometer is used to determine the temperature difference between a mixture of ice and water and liquid mercury at approximately 600 degrees Celsius. Complete figure 5.1 with a labeled diagram to show how the thermocouple thermometer can be used in this way. So very simply, we just need to draw a thermocouple thermometer. What we're gonna draw first of all is we're gonna draw over here an ammeter. Let's say we're drawing an ammeter, or even a galvanometer works. If you want to draw a galvanometer, you will just draw it like this, okay? But let us say that we are connecting an ammeter. Then from the ammeter, we will connect what? We will connect 2 wires over here that are from the same material, and 1 wire over here that is of different material. So let me just extend these wires. So these 2 wires, they are from the same material, and 1 wire over here that is from a different material. So what you can see over here is that this is junction 1. So junction 1, it is in the mixture of ice and water. And junction 2, it is in the liquid mercury, which is approximately 600 degrees Celsius. So what's gonna happen? It's gonna detect the change in temperature, or the difference in temperature, and then an electric current will flow. Okay, let us move on to part B. State 2 other physical properties that can be used to measure temperature. If we're thinking of a thermometer, for example, what happens in a thermometer? The liquid either expands or shrinks. So you can say the expansion or shrinkage, because these are the same thing, or shrinkage of liquid, which is in most cases mercury. And if we are also thinking of the thermocouple, what's happening in the thermocouple? There is what electrical resistance happening. So you could put the other option as what? As electrical resistance. Now, other options you can put is the expansion of a solid, the expansion of a gas, and the density of liquid. Okay, these are all physical properties that can be used to measure temperature, or they are thermal properties. So they said, state 2 benefits from using a thermocouple thermometer instead of a liquid in glass thermometer. So you have many different benefits. You have, first of all, that a thermocouple thermometer has what? A smaller capacity. A smaller thermal capacity, smaller thermal capacity. Okay? If it has a smaller thermal capacity, that means the slightest change in temperature will cause a current to flow. So it's more sensitive. It can detect any small change. The second thing we could put is that it has a large range. That means the liquid in glass thermometer, it might explode if you put it, or it might like break if you put it in very high temperatures, or it might even shrink and explode as well if you put it in very cold temperatures. So whereas the thermocouple, it would not happen if you put it in high temperatures and low temperatures. So it can go from a very low temperature to a very high temperature. Some other benefits, they are, it can measure high temperatures, it is very remotely sensing, it has a small size, it is suitable for data logging, and it responds quickly, and it measures the rapidly varying temperatures quickly. Okay, let's move on to the next question. The next question is from a new paper, or not a new paper, no, it's from the same paper, my bad. Okay, it's from the same paper. It shows particles of a material in which a sound wave is traveling. They said, on figure 6.1, mark the center of a compression with the letter C. Okay, so compression is definitely the dots with the smallest gaps in between them because they are being compressed. So over here, we have C, C, and C. These are all compression. Now they want the center of rarefaction with the letter R. So you're going to choose the ones where they are greatly expanded. Okay, so I'd say also here a little bit. So it's gonna be R, 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 and R. And then they said one wavelength with a double-ended arrow. Okay, so look what they mean. They mean, first of all, that if it's rarefaction, it's gonna go down as the wave. Okay? And it's gonna be a little bit longer. So if it's rarefaction, it's going down. Then compression, it goes up. Then rarefaction, it goes down. Then compression, it goes up. Rarefaction, it goes down. Compression, it goes up. Rarefaction, it goes down. Okay? Now, I don't know what they mean by double-ended arrow. Let me just check. Oh, so the double-ended arrow goes like this. So it starts from here, and it also can happen from here. So anyways, remember, when you're drawing the wavelength, okay, you're going to have that rarefaction is going to be the lowest point, whereas compression is going to be the highest point. Okay, I'm a bit unsure about this one, so please double check with your teachers. Let's move on to the next question. So question part B. Circle one value from the list, which is the speed of sound in water. Okay, let me just check. Okay, so here I don't think there is a way to solve it. You just have to know that the speed of sound in water, it is 1,500 meters per second. Because why? We will use it in the second equation to solve it. Okay, so for part B, they said the wavelength of the sound. So, okay, for part B, you should memorize that it's 1,500 meters per second. So you can solve part C. In part C, they said the wavelength of a sound is 12 centimeters, which is 0.12. This is 0.12 meters. They want us to calculate the frequency of the sound wave using your value from part B. So if that's the case, then we'll apply the equation that frequency is equal to the speed over the wavelength. So the speed, which is 1,500 meter per second, you're going to put it over 0.12 and you will get 12,500. Now you want to put it to two significant figures, it will be then 13,000. So the frequency is 13,000 hertz. Okay? So they can explain whether the sound in part C is ultrasound. You should memorize that ultrasound, it is what? It is greater than 20,000 hertz. So definitely it's gonna be, no, it's not gonna be the 20,000 hertz. Explanation is that ultrasound, it is what? It is greater than 20,000 hertz. And the thing we have over here, it is what? It is 13,000 hertz, which is less than 20,000 hertz. We move on to the next question, which is question number 8. They said figure 8.1 shows a conducting object A, initially uncharged, held on an insulating stand that the positively charged rod B is brought close to object A. On figure 1, draw the distribution of charges. So it's positively charged, that means the negative charges are going to be moving here, okay? And then the positive charges, they are going to be moving here, but they have to be the same number. So I put 1, 2, 3, 4, 5, 6, 7 negative. So 1, 2, 3, 4, 5, 6, 7 positive, okay? But the negative is going to be closer to the positive side, okay? A wire is connected from object A to Earth. State and explain any movement of charge. The statement is that the negative charges of the Earth, they will flow up, okay? They will flow up to the object. So negative charges of the Earth flow to object. Explanation. Why do they flow from the Earth to the object? They flow from the Earth to the object to balance the charges, okay? So to balance the charges, mainly the positive charges. So look what's gonna happen. You will earth it. So the negative electrons from the Earth, they're gonna go to the conducting object, okay? And then they are gonna balance out the positive over here, because here, look what's happening. These positive are balanced out by the negative, okay? And these positive, they need to be balanced out by something. So they are balanced out by what? By the Earth electrons, okay? We move on to part B. Part B, it said that the current, there is a current in the wire of 0.65 milliamperes for 2.2 minutes. Calculate the charge that flows. We know that the charge, it is equal to what? It is equal to the current. So charge Q is equal to the current I times the time T. What is the current I? The current I is 0.65 milliamperes. So change it to ampere. It is 0.65 times 10 to the power of minus 3 multiplied by the time, which is 2.2 minutes. You need to change it into seconds. So 2.2 minutes times 60 seconds. So put it together on your calculator. 0.65 times 10 to the power of minus 3 times 2.2 times 60. You are going to get 0.086, because you need to add two significant figures based on this one and this one. Okay, we move on to the next part, which is question 9. In question 9, it says figure 9.1 shows a cell of electromotive force, okay, 15 volts, and a battery of electromotive force 6 volts. Calculate the combined electromotive force of the cell and the battery. So because they are all facing the same direction, where positive comes before negative, so positive, negative, positive, negative, they become additive. You add them together. So it's 1.5, and first of all, because they are in series. So it becomes 1.5 plus 6. You will get what? That the electromotive force is 7.5 volts. Okay? We move on to part B. The combined resistance of the three resistors as shown in figure 9.2 is 4.4 resistance, or 4.4 ohm. Calculate the resistance of resistor R. So we know that resistor R plus the equivalent resistance of this over here. How do we find the equivalent resistance? It will become 1 over 2 plus 1 over 3. This is equal to 1 over 2 plus 1 over 3, it is equal to 5 over 6, but now you need to flip it. It will become then what? It will become 6 over 5. So the resistance R plus 6 over 5 is equal to 4.4 ohm. Okay, so very simply 4.4 ohm minus 6 over 5, you put it on your calculator and you are gonna get that the resistance R, it is equal to what? It is equal to 3.2 ohm, very simply. So the resistance R over here, it is 3.2 ohm. We move on to part 2. The current I in figure 9.2 is 0.94 ampere. Calculate the potential difference across the combination of resistors. So we know that the equation is V is equal to the current times the resistance. We know that the resistance or the net resistance is 3.2 ohm. So it will become 0.94 ampere times 3.2 ohm. Put it together. And you are gonna get, oh sorry, my bad. This is the resistance of resistor R. The net, the combined resistance is 4.4. So my mistake, this one over here is not 3.2, it is 4.4 ohm. So 0.94 times 4.4 ohm, you're gonna get it to be approximately 4.1 volts, okay? So we finished from this question. We'll move on to the next question, okay? The next question is a new past paper. So we start with question number 2. They said, define the moment of a force about a point. The moment of a force about a point. We need to define it. Okay, it is the force multiplied by the perpendicular distance, by the perpendicular distance from the point. So very simply, this is the definition of a moment. It's the force multiplied by the perpendicular distance from the point. We move on to figure 2.1. Figure 2.1 shows a uniform rod of wood suspended from a pivot. The rod is held stationary by a horizontal force F acting as shown. The mass of the rod is 0.08 kg. Calculate the weight of the rod. Very simply, it's 0.08 kg times 10, which is the G. You are gonna get, because we know W is equal to mg, we have the mass over here, and usually here they will use the G as 10, so it becomes 0.08 times 10, which is then 0.80 Newton, so the weight is 0.80 Newton. We move on to part 2, the moment of W about the pivot. So look, where is the pivot? The pivot is over here. We need to find the moment of W about the pivot. So remember that the weight, we found it to be how much? It is 0.80 Newton, okay? This is what? This is the force, so we already have the force. The only thing we need now is the perpendicular distance from the weight to the pivot, which is given over here to be how much? To be 0.25 Newton. So it's gonna be 0.80 Newton times 0.25 Newton. You multiply it together, you're gonna get an answer which is approximately 0.20 Newton per meter. So the moment, okay, of W about the pivot, it is 0.20 Newton per meter. We move on to part 3, the moment of F about the pivot. Let us go down. The moment of F about the pivot, we know what? That it is balanced, okay? It is held stationary, meaning it is balanced. If it is balanced, then that means all of the forces downward, which is only the weight, is equal to all of the forces upward, which is the force of friction F, and definitely the upward resistance. But in this case, they're gonna take only what? They're gonna take the force of F as what? As the upward, as the only upward force. So now all the forces downward, which is W, is gonna be equal to all of the forces upward, which is F. But then they're not gonna have the same exact force, okay? So we can take it as all of the moments that is counterclockwise is equal to all of the moments that is clockwise. Okay, so you could say that the moment of the weight, which was 0.20 Newton, is going to be equal to the moment of F. So in this case, we now have what? We have that the moment of F is going to be the same as the moment of W, because it is the force that is counteracting it. Now, to find the value of the force F, we know that to find the moment, it is equal to what? It is equal to the force F multiplied by the perpendicular distance from the pivot. The perpendicular distance from the pivot, it is 0.75 meters. So times 0.75 meter, and you will get that F is equal to 0.75, 0.20 over 0.75. So you put it on your calculator, 0.20 divided by 0.75. You're going to get an answer which is approximately what? It is approximately 0.27 Newton. So the force F is equal to 0.27 Newton. We move on to the next question, which is question number C. The angle between the rod and the vertical is increased. So you are increasing what? The angle in between the vertical and the rod. Okay? So we will move on. They said state whether the force F needed to hold the rod stationary must be increased or stay the same. Explain your answer. So if we are increasing the angle, I think they mean like to increase the angle like this. Okay. If you are increasing the angle, then let's say that the new one will be like over here. Okay. You're gonna have that the moment, or not the moment, the distance from the weight or the center of the mass, okay, and the pivot over here will increase. So this distance over here, it increases. Okay, so look, we know that it is distance perpendicular times force W. So if the distance perpendicular increases, that means the force W needs to decrease. But logically speaking, can you decrease the weight of an object? Can you like decrease unless you cut it? Definitely, for sure, you cannot. So what's gonna happen is that we will need to change the moment of F. We're gonna need to change both the force and the direction of F in order to balance it. So what's gonna happen to F now? What's gonna happen to F is that the perpendicular distance from the pivot is gonna decrease. So if the distance perpendicular decreases, that means the force F is gonna increase. Okay, so very simply, what we could say over here, we could say that as the perpendicular distance from the pivot to F decreases, okay, the force F will need to increase for a greater moment. Why do we need a greater moment? Because as we said, the distance will decrease, but the mass will stay the same. If the distance decreased and the mass or the force stayed the same, that means that it's what? It is gonna decrease the, the distance increased. So from the weight W to the pivot, the distance increases, but the weight stays the same. Sorry for that. So the perpendicular distance from the weight to the pivot increases, so the weight stays the same force. So that means what? The moment of the weight will increase. That means we will also need to increase the moment of the force F for them to be the same. Move on to the next page, okay, which is question number 4. It says figure 4.1 shows a thermometer, okay. We have wire of material A, wire of material B, ice cubes, water, and a voltmeter. They said state the name of this type of thermometer. This type of thermometer, it is a thermocouple. Okay. Figure 4.2 shows the same thermometer used to measure the temperature of liquid X. With the setup in figure 4.2, the voltmeter is 1.7 millivolts. Calculate the temperature of liquid X measured by the thermometer. So the equation is what? Is the one second. So I think we have to get something from up. Ah yes, over here the voltmeter is 5.4 millivolts. If the distance is what? If the difference in the two temperatures, it is 100 degrees Celsius, okay? So it became 1.7 millivolts, so it becomes 1.7 millivolts over 5.4 millivolts times what? Times the change in temperature from here to here, which is 100 degrees Celsius. You will put it on your calculator, 1.7 over 5.4 times 100. You're gonna get an answer which is approximately 31.5 degrees, but let us just take it as 32 degrees, okay? Or more realistically, I think let us take it as 31 degrees, okay? So this is gonna be the change in temperature. So what you're gonna do is that you're gonna take the 20 degrees Celsius and you're gonna add to it the 31 degrees Celsius to get the new temperature, which is 51 degrees Celsius, okay? So we'll move on to the next question. This question over here says, suggest an application for which this type of thermometer is more suitable than a liquid in glass thermometer. So we could say if there is any rapidly changing temperature, if there is any rapidly changing temperatures. Okay, other things you can put is higher or lower temperatures, rapidly changing temperatures, vibrating machinery, remote sensing, or data logging, or small areas and masses. We'll move on to this one over here. So question number 5, define specific latent heat. So specific latent heat, it is what? It is the thermal energy, okay, needed to change the state of 1 kilogram of material. But we do not say per degrees Celsius. Why? Because when you are changing the state, there is no change in temperature. So the specific latent heat is the thermal energy needed to change the state of 1 kg of material. We move on to question number 2. Explain the melting of a solid in terms of molecules and energy. So what happens when we are melting a solid? When we are melting the solid, the molecules must be separated, or the intermolecular bonds must be broken. So intermolecular bonds must be broken, okay? And to break the bonds, we need energy. So energy is needed to break the bonds. So very simply, you get your 2 marks like this. Intermolecular bonds must be broken. Energy is needed to break the bonds. We move on to part B. In part B, an electric heater is used to heat a liquid to its boiling point. Figure 5.1 shows the apparatus. Okay, you have connecting wires, heater element, balanced liquid container. When the liquid is boiling, the heater supplies 1.2 megajoules of thermal energy. The mass reading shown on the balance decreases from 3,800 grams to 2,300 grams. Okay, so they need the mass reading shown on the balance decreases from 3,000 grams to 2,300 grams. They want us to calculate the specific latent heat of vaporization of the liquid. Very simply, the equation is that the energy, which we found over here, is equal to the mass multiplied by the specific latent heat. So let us find the mass together. To find the mass together, you're going to take these two values and you're going to subtract. So 3,800 grams minus 2,300 grams. So you're going to get 1,500 grams. Okay. Now you need to change this into kg. Do not forget. So it will become 1.5 kg. Okay, and then we have the energy, so we can find the specific latent heat. So it will be 1.26 megajoules. So that's 1.26 times 10 to the power of 6 is equal, this is 10, is equal to 1.5 kg times the specific latent heat L. So L is equal to what? To 1.26 times 10 to the power of 6 divided by 1.5. So you're gonna get an answer which is approximately 8.4 times 10 to the power of 5 joules per kg. So over here it is what it is, 8.4 times 10 to the power of 5 joules per kg. We'll move on to question part C. State and explain a precaution to improve the accuracy of the value of specific latent heat calculated in B. You can insulate the container to prevent any heat losses. Okay, we'll move on to the next paper. The next paper is question number 6. Okay. Okay. In question number 6, it says, figure 6.1 shows a transverse wave produced by a spring. Draw labeled lines to show the amplitude of the wave, the wavelength of the wave. Okay, so to find the amplitude of the wave, what you're gonna do is you're gonna take from the end of the spring till here, you are gonna separate it, okay, into the positive side and the negative side. And then this value over here, this is our amplitude. So of course do it more accurate with the ruler, but I'm just giving you a general idea of how to do it. Now the wavelength, you always take the wavelength from crest to crest, so it can be over here, or even from trough to trough, so it can be over here. Okay, label a trough with the letter T. Let us say this trough with the letter T. A person vibrates one end of the string vertically to produce the wave. He makes 15 complete oscillations in 60 seconds. Show that the speed of the wave is 2 centimeters per second. Okay. So very simply here, what we need to do is we need to use our ruler. So with our ruler, we will measure the distance between these two, okay? And we will find that it is it is 8 centimeters. So keep this in mind. You need to bring a ruler with you, okay? A person vibrates one end of the string vertically to produce the wave. He makes 15 complete oscillations in 60 seconds. So we need to apply the equation that frequency times the wavelength is equal to the speed. So we have the wavelength, which is 8 centimeter, okay? It's equal to the speed, V, times the frequency. Let's find the frequency together. We know the frequency, it is how many oscillations it can make in 1 second. So it becomes 15 over 60 times 8. So you will get that the velocity is 2 what? Because it is in centimeter, 2 centimeter per second. Okay, we move on to part C. Part C says, state the difference between transverse waves and longitudinal waves. Use your ideas about the direction of oscillation. Okay, transverse waves, okay, they travel or they move, oscillate perpendicular or normal to the to the direction of propagation of the wave, to the propagation direction of wave, direction of wave. Then we move on to the longitudinal waves, and the longitudinal waves, we know that they move parallel or along to the propagation direction of waves. Okay, we will move on to the next question. Now, the next question is question number 9, okay? In question number 9, figure 9.1 shows a bar magnet and 4 plotting compasses A, B, C, and D. Draw an arrow on each of the 3 plotting compasses B, C, and D to show the direction of the magnetic field. As you can see over here, the magnetic field is going to which direction? It's going to this direction. That means from here, it is going how? Based on A, it is going the magnetic field like this. And if it's going like this, and we know that inside it flows from the South Pole to the North Pole, then that means that the left side is the South Pole and the right side is the North Pole. Now from outside, they are going from the North to the South. Now we can complete their direction. We know that C will follow the South to North, so it will go in this direction. So it will follow this magnetic field over here, whereas B and D will follow these magnetic fields over here. This one and this one. So it's going to the left, so you will draw it to the left, and this one is going to the left, so you will also draw it to the left. So now we move on to figure to the next question. They said label, okay, we already did them. Okay, so we did I and II together. Okay. Describe one method for demagnetizing a magnet bar. So you could heat a magnet. Okay. You can heat the magnet by changing it to, like, by exposing to really high temperatures. Okay, this is one way. We move on to part C. We have draw the pattern of the magnetic field produced around the wire, so clearly the direction of the magnetic field. Okay, so what we're gonna do over here is, we know that what? This over here, I believe it is the current I. So what we're gonna do first of all is we're gonna draw 3 circles. So 1, 2, 3. This shows what? The magnetic field. Now what we're gonna do is we're gonna do the right hand rule. You're gonna take your thumb, you're gonna put it facing towards the screen because the current is going inside, and then you're gonna rotate your the rest of your fingers, and you will see that the magnetic field is going in this direction. This direction is what? This direction is the clockwise direction. Okay? For number 2, the direction of the current in the wire is reversed. If it is then reversed, then the magnitude of the current is unchanged. If the magnitude of the current is unchanged, that means the magnetic field is going to stay the same amount. Okay, but if the current is reversed, then that means it's going to be facing to you, not to your screen anymore. So your finger is going to be pointing away from your screen. Then that means what? The magnetic field is also going to reverse. Okay, so we will now move on to the next question. The next question is question number 10. Okay, question number 10, part A. A student composes the circuit and measures the current in the 6 ohm resistor. On figure 10.1, draw an ammeter symbol in one gap and straight lines to indicate wires in the other gaps to show how the student should do this. Okay, so definitely the current in this wire over here is going to be the same as the current in this wire over here. So what's going to happen is that if we put an ammeter over here, then for sure we will be able to measure the current that is coming to this resistor. Okay, we move on to part 2. A voltmeter is connected to measure the potential difference across the 4 ohm resistor. Draw a voltmeter. You should draw it parallel, okay, to the resistor. So that means you will put it over here. This is the voltmeter. Part 3. With the current completed, the current in the 2 ohm resistor is 2.5 amperes. Calculate the current in the 6 ohm resistor. Okay? So the first thing we're gonna do is we're gonna find the voltage across what? Across the this one over here. If we find the voltage across this one over here, then we will be able to find what? To find the current that passes over here. Okay? So very simply, the voltage, it's going to be equal to 2 ohm times 2.5 ampere. So the voltage is then 5 volts. That means the voltage over here is also going to be 5 volts. So that means the current that is going to go through the 4 ohm, it is equal to what? It is equal to the 5 volts divided by the 4 ohm, which is approximately 1.3 ampere. So now we have what? We have the current over here as well, which is 1.3 ampere. If this one was 2.5 ampere and this one is 1.3 ampere and we add them together, okay, then we are going to get a value of 3.8 amperes. And now, since we added them together, we got the value of this current and this current very simply, which is 3.8 amperes. We move on to the next question, which is question 10. So figure 10.2 shows the same electrical circuit with an alternating current power supply and the wire in gap A. Okay, and figure 10.2, draw a diode symbol in one gap and a straight line to indicate a wire in the other gap. So there is a current from the right to the left in the 4 ohm resistor and an alternating current in the 2 ohm resistor. Okay, so what does the diode do? I believe the diode will change the alternating current into a direct current. So there is a current that will go from the right to the left, okay, in the 4 ohm, so it will change the direction of the alternating current. Okay, that will make it then a direct current. Whereas here, you can draw a wire, and you can see what? You can see that you will get an alternating current. Very simply, that is it for this question. We'll move on to the next one. They said state two differences between nuclear fission and nuclear fusion. Nuclear fission is what? Fission, it is the splitting of the nucleus into two atoms. So the nucleus splits into two atoms, whereas the fusion, okay, nuclear fusion, is that two atoms combine to form a nuclei. Two atoms combine to form nuclei. Okay, we move on to part B. Part B says radioactive tracers emitting gamma rays can be used in medicine. The half-life of the source of the X-ray, not the X-ray, the gamma ray is 6 hours. Explain why a source of gamma ray used in this way should not have a half-life shorter or longer than 6 hours. If we choose something that has a longer half-life, okay, this could result in the radioactive substance causing poisoning or radioactive poisoning in the human. So it's very radioactive. So radioactive substance for a long time in the body. Substance for a long time in the body. Okay? Whereas the shorter half-life will be insufficient, so not enough time, so insufficient time for investigation. So this is very simply part B. We move on to part number 2. Technetium-99 is a source of gamma ray often produced as a radioactive tracer. It's produced from molybdenum, I don't know, whatever this is, 99, which emits beta particles. The symbol for technetium Tc and the symbol for whatever that is Mo. Complete the nuclide equation for this decay. Because it releases a beta particle, that means you're going to have 0 as the mass and -1 as the charge, okay? So over here, the mass is going to stay the same, which is 99, whereas the number of protons is going to increase, and this is going to become 43. Now, this is a radioactive nuclei state. Another use for radioactive nuclei in medicine, for example, you could say sterilization of equipment. Okay, so very simply, that's it. We'll move on to 0625, the next past paper, so question number 2. State two conditions which must be true for an object to be in equilibrium. The two conditions must be that no resultant force, so the forces are balanced, so forces are balanced, aka in another term, the net force is equal to 0. And condition 2 is that the counterclockwise moment equals the clockwise moment. Okay, we move on to figure 2.1, shows a uniform meter rule PQ in equilibrium. The distance PQ is how much? PQ, the total distance, it is 100 centimeters. And the mass of the center of the ruler is how much? It is 0.12 kg, and its weight is W. Okay, they said draw an arrow to show the force W acting on PQ at the center of the mass. We already did it. And they said an arrow to show the force R acting on PQ at the pivot. Okay, they said by taking moments about the pivot, calculate the value of F. So we need to calculate the value of the force F. They said the pivot is what? Which is the pivot? I think the pivot is over here. Yeah, the pivot is over here. So first of all, we have this force over here, which is 0.50 Newton. 0.50 Newton. From the pivot, is it going clockwise or counterclockwise? You will put your palm, first of all, facing the pivot, and then your fingers pointing to the direction of how it is pointing. So it is pointing down, that means your fingers will need to be pointing down and your palm will be facing the pivot. You will see that it is pointing outside. So if it's pointing outside, then directly it is positive, meaning it's gonna turn counterclockwise, okay? So 0.50 times the distance, which is 10 centimeter, okay? It is equal to what? It is equal to, first of all, the pivot, the force of the pivot is gonna be, it's not equal, sorry. Plus the force of the pivot, which is 0, because the pivot with respect to the pivot is 0, okay? Plus the force of the mass. We know, first of all, it's 0.12 kg, so if you make it into newtons, it becomes 1.2 newton. Let me just change the color. So 1.2 newton multiplied by the perpendicular distance from the pivot, which is 40 centimeter. But now we need to see, is this plus 40 centimeter or minus 40 centimeter? To see if it's plus or minus, we're going to do the right hand rule again. So our fingers will be pointing down and our palm has to be facing the pivot. You will see that your thumb is pointing towards the screen, so it's going to be minus 40. Okay, and then we are going to add it to the force, what? To the force F multiplied by the perpendicular distance, which is what? Which was 100 centimeters. Okay, now if we apply the right hand rule, you will see that your fingers will be pointing up, your palm will be facing the pivot, and it's pointing outside, so it is gonna be positive. All of this is equal to what? It is equal to 0. So very simply, it will become 0.50 times 10, which is 5 Newton per centimeter, plus 0 plus 1.2 times minus 40. This is minus 48 Newton per centimeter. And then, in addition to what? In addition to the force F times 100 centimeter is equal to 0. So add these two together, you're gonna get 5 minus 48, it's gonna be minus 43. Okay, so minus 43 Newton per centimeter plus F times 100 centimeter is equal to 0. Bring this to the other side. F times 100 centimeter is equal to 43 Newton per centimeter. So divide both sides by 100, you will get that F is equal to 0.43 Newton per centimeter. So very simply, the answer over here is 0.43 Newton per centimeter. They want us to calculate R. To calculate R, we know very simply that all the upward forces are equal to all of the downward forces. So what are the upward forces? The upward forces are R plus F. They are equal to the downward forces, which are the 0.50 Newton plus the 1.2 Newton. Okay, so R, we need to find it, plus F, which is 0.43, is equal to 0.50 plus 1.2. Okay, so R is then equal to 0.5 plus 1.2, which is 1.7. Bring 0.43 to the other side, minus 0.43. You will get your answer, R, to be 1.27 Newton. Or if you want to put it to significant figures, it is 1.2 Newton. Move on to the next question. Let me check how many we have left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 more pages. Okay, we can do it. So, question number 5. One difference between a longitudinal wave and a transverse wave is that a longitudinal wave consists of compressions and rarefactions. Explain the term compression and rarefaction. First of all, what is a compression? A compression is when the particles are closest together. Particles are closest together, or are closer together. You can say closer together. And the rarefaction is when the particles are farther apart. Particles are farther apart. We move on to number 2. Describe one other way in which longitudinal wave motion differs from transverse wave motion. We know that longitudinal wave motion, it moves parallel to the direction of propagation, to direction of propagation. Okay. Then we have the transverse wave motion. It moves perpendicular or normal to the direction of propagation. Okay, we move on to part B. A sound wave of frequency 0.120 kilohertz travels through a rock of speed at 3,500 meters per second. Calculate the wavelength of the wave. We know that wavelength is equal to the speed over the frequency. So it's going to be what? It's going to be 3,500 meters per second over the frequency, which is 0.120 kilohertz times 1,000. So it is 120 hertz. So we put it on top of each other, 3500 over 120. You will get it approximately to be 29 meters. Okay, we move on to question number part 2. The wave travels from the rock into the air. State and explain the wave, whether the wave will be audible to a healthy human ear. So remember, when it is going from substance to substance, so it's undergoing refraction, then the frequency stays the same. So frequency stays the same. I think this is the explanation. 1 second. This over here is the explanation. Okay, and yes, it is audible. So the frequency stays the same, meaning that the frequency is between 20 hertz and 20 kilohertz. This is important because humans can hear 20 hertz to 20 kilohertz. Okay, we move on to question number 7. Question number 7, it says, it shows a coil of wire wound around a thin plastic cylinder. The plastic has no effect on any magnetic field. The galvanometer is extremely sensitive. Okay, a magnet is fixed to a small trolley that runs without friction on a track through the cylinder and coil. The trolley is released from point A, so it runs through the coil from the right to the left. State and explain what happens. Okay, so what's gonna happen? State and explain what's gonna happen. There's gonna be some deflection in the galvanometer. Okay, so it's gonna move a little bit. Why? Because there was a change of magnetic flux. So change in magnetic flux. This change in magnetic flux causes the induced current, so it will cause the deflection of the galvanometer. Okay, we move to part 2. The trolley is now released from point B, so it runs through the coil from right to left. State what is observed on the galvanometer and explain why it is different to your answer in part A. Okay, if it moves from the right to the left, okay, but this time it is released from point B. Okay, so it is released from point B. Because it is released from point B, it's gonna have what? It's gonna have a higher speed, okay? And since it has a higher speed, that means it will have a larger deflection. Okay, we move on to figure 7.2. It shows an extension LED used to supply a power to a 3 kilowatt electric heater on a cool evening. Okay, state and explain 3 dangers with this experiment. Damp grass means we have some water. Okay, so it could cause what? It could cause the actually, you can just write this as a hazard. Okay, so you have that it is placed, the wire is placed on what? On damp grass. So the water could get in and could cause an electric shock. Okay, the next thing that could happen is that so because the wire is placed on the damp grass, what could happen? There could be way too much like current, so it could be current is too high, and if it is going from a very high current placed on the damp grass, what will happen? We will have a cut in insulation. Okay, this is the first thing that could happen. The second thing is that it is a tripping hazard, so trip hazard. And then the third thing is that electrocution could happen. Why? Because there is a cut in the outer insulation, so there could be electrocution could happen. So very simply, we have that 3 dangers with this wire arrangement is that the wire is placed on the damp grass, and if the current is too high, there can be a cut in the insulation. It is a trip hazard because the electrocution, it's a trip hazard because it's a long wire, and electrocution could happen because of the cut in the outer insulation. Okay, we'll move on to question number 7. So figure 7.1 shows a small plotting compass which is aligned with the magnetic field between magnetic poles A and B. State the polarity of the poles. Okay, the north is pointing here, the south is pointing there. So pole A is gonna be the north pole because it will attract the south pole, okay? And point B is gonna be the south pole because it will attract the north pole. So pole A is north and pole B is south. Figure 7.2 shows a wire placed between the two poles carrying a current in the direction. On the field, draw an arrow to show the direction of the force of the wire due to the magnetic field. We know that the magnetic field will move from the north to the south. So your current, your thumb, we're gonna do the right hand rule. Your thumb is gonna go with the current to the right. Your index finger is gonna go north to south, which is down. And then your middle finger is gonna be pointing vertically upwards. So it's vertically upwards. Okay, we move on to the next question, which is part C. Figure 7.3 shows a beta particle moving in one direction of arrow between the same two poles. Draw an arrow to show how the direction of the force will change due to the magnetic field. So the magnetic field is going from the north to the south, okay? So you're gonna take your thumb and you're gonna put it from the north to the south inside, and then you are gonna curve your finger. Okay, so curve your finger and you will see that the deflection will happen like in this direction. So it's going to be pointing downwards, okay? Or vertically downwards. You can say it's going to be pointing vertically downwards. We move on to the next question, which is question number 2. They said define the moment of a force. What is the moment of a force? The moment of a force, it is what? It is the force multiplied by the perpendicular distance from the pivot, distance from a pivot. Okay, we move on to part B. Figure 2.1 shows an object of negligible weight. The object is in equilibrium. The object is free to rotate about its pivot P. Calculate the value of force F. Okay, so force F over here, we need to find its value. But also, what we should know is that the tension everywhere is gonna have the same value. So if this is 50 kg, which is 500 Newton, then the tension over here is also gonna be 500 Newton. Okay, and now, very simply, we can find what? We can find the force of F by doing that moment clockwise is equal to moment counterclockwise, okay? So the moment clockwise, it is 50. Of course, I don't know what they are. I'm just stating anything. So 500 newtons times what? Times 20 centimeter. It is equal to what? It is equal to the force F times 12 centimeter. So F is equal to 500 over 20. Sorry, 500 times 20 over 12. Put it on the calculator. So then we get that the F is approximately, because I think they might need it to two significant figures, it is F is approximately 830 newtons, okay? We move to part C. They said describe an experiment involving vertical forces to show that there is no net moment on an object in equilibrium, okay? They said, okay, so we could take, for example, the example of a seesaw, okay? You take the seesaw, you will have, for example, a person over here who weighs 100 Newton, okay, and the distance from here to here, 100 times. Okay, let's say the distance from him here to here is how much? It is 200, it is 2 meters, okay. So 100 Newton times 2 meters, and then we have another person on the other side. They weigh how many? They weigh 200 Newton, but the distance from them over here, it is 1 meter. Now we will calculate what? Moment clockwise plus moment counterclockwise, and you will see that it is equal to 0. So the net moment is equal to 0, very simply. We'll move on to the next question. So figure 7.1 shows two magnets and the gap between the North Pole and the magnet of the South Pole on the other. Draw 3 lines to show the pattern and direction of the magnetic field in the gap. First thing, we have from north to south. So it will flow outside from the north to the south. Okay, because they are asking for the magnetic field, we will not do anything inside. So we could just draw it like this. You can draw 3 lines from the north to the south. Okay, middle line must be straight and perpendicular. Oh, okay, so they drew it like this. Look, the middle line is straight and perpendicular, then north to south, north to south. This works totally. Okay. The next thing we have is part B. Figure 7.2 is a repeat of figure 7.1. Draw the position of a plotting compass when it comes to rest in the gap between the north and south pole. So you will put the plotting compass over here. Okay. You will have that the needle will follow the direction of the magnetic field. The magnetic field goes from the north to south. So the needle will go from where? From the north to the south, like this. So very simply, this is the arrow. It is pointing towards the south pole. Explain why the needle comes to rest in this position. Why does it come to rest? It is because the needle, okay, needle aligns with the what? With the magnetic field. Okay, so the needle will align with the magnetic field. We move on to part C. Describe a method of demagnetizing a bar. You could heat it, you could hammer it, you could place it in a solenoid with an alternating current, or you could withdraw or reduce the current to 0. This is if we're dealing with an electromagnet, but most probably heat. You can expose it to high temperatures. Okay, we move on to the next question. Let me check. We have 1, 2, 3, 4 pages left. Great, that's good. Okay. So, a student makes a transformer that uses an alternating current AC supply with an electromotive force of 12 volts to induce an output potential difference of 2 volts. The student is provided with 2 lengths of insulated wire and the U-shaped piece of iron shown in figure 7.1. Complete and label 7.1 to show the transformer connected to the supply and output of the transformer. I think here we will do it like this. We will draw here is the supply. Okay, it is connected, and then this is the wire. I think the wire should go from up. So it's connected like this, okay? And then we will have what? Magnetic field will go here from the North Pole to the South Pole. And here we will have the other wire that will go what? To the output. Very simply, this is how you're supposed to draw it. We move to the next one. Explain the function of the piece of iron. Oh, I forgot that there's supposed to be a piece of iron over here. Do not forget this. This piece of iron, it is soft iron. What does it do? It links the magnetic fields together. Links magnetic fields together. Okay, and it will like form a better induction of the magnetic field. Okay, the output of the transformer is connected to a lamp. The current in the lamp is 100 milliamperes. The transformer is 100% efficient. Calculate the input current of the transformer. Okay, so the power 1 is going to be equal to power 2. So power 2, they said that it is how many ampere? It is 100 milliampere. So 100 milliampere, it is 0.1 ampere. Multiplied by the voltage. What is the voltage secondary? It is 2. So 0.1 times 2, it will be what? It will give us an answer of 0.2 watts. So the power is 0.2 watts. So if you come over here, you know that the voltage over here is 12. So 12 volts times the current A is equal to 0.2 watts. So now it's going to be 0.2 watts over 12. So you will get it approximately to be 0.017. So the current, it is how much? It is 0.017 amperes. We move on to part B. Another transformer is used in a school laboratory to step down a main supply with a potential difference of 110 volts to 12 volts. This transformer is mounted in a metal case. State and explain an essential safety feature required for this. You should earth the metal case, because there might be the charges flowing on the metal could cause electrocution. So earth the metal case, okay? So we move on to the next one, which is question number 3. Figure 3.1 shows solar panels used to generate electrical energy. State the main form of energy transferred from the sun to the solar cells for the generation of electrical energy. This is light energy, okay? Consider the generation of electrical energy by a large number of solar cells as shown in figure 3.1. State one environmental advantage and one environmental disadvantage. An environmental advantage is that there is no air pollution. An environmental disadvantage is that it takes up land. So it will basically like be wasting the land and destroying habitats, okay? State and explain whether this source of electrical energy is renewable. Yes, it is renewable. Why is it renewable? Because nothing is used up. Yes, nothing is used up. Okay, we move on to the next page. Each group of solar cells is arranged in a rectangle of 1.2 meters times 2.8 meters. The solar cells are situated in a region where 260 watts of solar energy is received per square meter of the cells. The electrical output of each group of solar cells is a current of 2.5 amperes with a potential difference of 86 volts. They want us to calculate the efficiency of the solar cell. We know that it's power 2 over power 1 times 100. Okay, so they are situated where? We can find what? We can find power 1. Power 1 is what? Power 1 is equal to 260 watts times what? Times the this area, which is 1.2 times 2.8. So 260 times 1.2 times 2.8, this will give us almost 870 watts. Okay, now that you have it to be 870 watts, this is power 1. Then we need to find the power 2. Power 2 is going to be very simply the voltage, which is 86 times the current, which is 2.5. So 86 times 2.5, it is what? It is 215. So they rounded it to two significant figures, so 220. 220 over 870 times 100%. Okay, so 220 over 870 times 100%, you're gonna get that it is approximately almost an efficiency of 25%. Okay, we move on to the last page. That's wonderful, the last page. Okay, it is question number 9. It says, describe how to demagnetize a bar magnet using an alternating current. So what you're gonna do first of all is you're gonna place the magnet in a coil. So place magnet in coil. The second thing you're gonna do is that you are gonna switch on the AC current. Switch on AC current. Okay, then after that you are gonna reduce the current to 0. And just like that, you will have demagnetized the bar magnet. We move on to part B. Figure 9.1 shows a simple direct current DC motor. Explain the purpose of the split ring commutator. The split ring commutator, what does it do for the direct current? It keeps the coils rotating, okay? It keeps the coils rotating by changing the direction of the current, okay? By changing direction of the current every half cycle, which is 180 degrees. So very simply, the split ring commutator will keep the coils from rotating by changing the direction, it will keep the coils rotating by changing the direction of the current every half cycle. Now the very last question, the voltage of the power supply is increased. State the effect this has on the motor. If the voltage is increased, then what happens? The coil rotates faster. So very simply, that is it for the past papers for physics. Thank you guys for watching. I hope you enjoyed and have a wonderful day.